Okay, let's dive right into this explainer. Imagine you're a paleontologist carefully digging through layers of dirt to reconstruct a massive dinosaur fossil. Well, tackling a Cambridge computer science question is kind of exactly like that. You've got to dig through the layers of the question to reconstruct the perfect, full mark answer. And we are starting off today by highlighting a massive trap where most students just completely lose easy marks on the current instruction register, or CIR, before they even begin their actual analysis. The principal examiner reports reveal a pretty hard truth. Candidates consistently confuse key terminology. So what's the golden rule here? Always, always define your terms before using them in your extended responses. If you skip this foundational layer, you are literally throwing away points right out of the gate.
Welcome, focused learners. Today, we are stepping directly into the mind of a Cambridge senior examiner. We're going to unlock the exact, no-nonsense strategies you need to master 9618 computer science CIR questions. We're not just decoding the current instruction register as a piece of hardware today. No, we are looking at it as a strategic framework for securing those top marks in your AS and A-level exams. I'm going to show you exactly what the examiners are looking for, and more importantly, exactly how to give it to them. To get us there, we'll logically unpack the core principles, reveal the standardized technical methodology, explore some advanced critical analysis, and finally, detail the top examiner warnings, the mistakes you absolutely must avoid.
Let's start with the foundational academic benchmarks for the current instruction register. We need to know, what does Cambridge actually demand from a top-tier candidate? This is absolutely crucial, and it brilliantly illustrates the dividing line between average and exceptional. Average candidates, they rely on superficial breadth. They try to brain dump every single fact they've ever memorized about special purpose registers, just kind of hoping something sticks to the wall. But the assessment framework heavily prioritizes analytical depth. Top-performing students are rewarded for demonstrating deep, connected, logical reasoning. It really isn't about how much raw data you can list, it's about how deeply you understand the specific mechanics of the CIR within the processor's cycle.
So the big takeaway here is that examiners aren't just looking for rote memorization. They actively want to see conceptual understanding that is so rock solid you can apply it to any unfamiliar scenario they throw your way. Whether the question introduces a totally novel processor architecture or a unique, weird instruction set, your mastery of the CIR's fundamental principles has to be transferable. That ability to adapt, that is the true hallmark of an A-grade student.
Let's move into our next section and see how this builds into the exact procedural framework needed to secure those vital method marks. Because, as you know, in computer science, the process is often just as important as the final answer itself. Now, what's really fascinating here is that this standardized 5-step sequence is literally the algorithmic thinking examiners use to grade your step-by-step decomposition. It's an algorithm for answering questions. First step, identify the key elements of the CIR in the prompt. Second, apply the relevant principles. Ask yourself, how does the instruction get here and where does the opcode go next? Third, execute your analysis with abundantly clear working. Do not skip steps in your head. The examiner can't read your mind. Fourth, verify your results through rigorous checking. And finally, step 5, present your answer in the appropriate format requested. Stick to this sequence and you've got a foolproof blueprint for method marks.
Let's look at how that methodology applies to data interpretation. Your answer really needs to seamlessly bridge 3 key areas. When you're extracting binary data from the CIR, you must accurately execute your calculations and then, and this is the part people forget, draw evidence-based conclusions. You can't just leave a binary conversion hanging there on the page. Explain what that specific opcode or operand actually means for the CPU's next operation. Does that opcode trigger a jump? Does the operand point to a specific memory address? Connecting these technical dots and presenting them in a highly structured format is exactly how you maximize your score. Having mastered the procedural steps, we now look at the higher-order objectives that separate a good answer from a truly exceptional one. This is where we get into critical analysis. It really all boils down to this one question. How do top scorers demonstrate evaluative thinking in complex CIR problems? To bump an average grade to a top-tier one, you have to employ what examiners call the deconstruct, solve, and evaluate framework. You break the given information down into logical pieces, solve it systematically, and then critically evaluate your own approach. Proper evaluation requires a few specific elements. First off, you need to consider multiple solutions or approaches. Next, analyze the trade-offs. You do this by identifying similarities and differences using comparative connectives. Words like whereas or conversely are great here.
You also must acknowledge the limitations of a given system or data structure. Nothing is perfect, and acknowledging that shows high-level thinking. And finally, justify every single decision or recommendation with hard evidence. This rigorous checking of your systematic solutions for reasonableness, that is exactly what secures those elusive, highest assessment objective marks.
Okay, before you face your next exam paper, we seriously need to address the direct warnings pulled straight from the principal examiner reports. These are the danger zones where the examiner's red pen comes out most often. Let's break down these top 3 traps. Trap number 1, the classic mistake of using the wrong formula or algorithm for the specific context provided. It's like using a hammer on a screw. It just doesn't work. Trap number 2, forgetting to check boundary conditions in edge cases. If the CIR is handling an instruction that pushes the absolute limits of the addressable memory, you have to note that. And trap number 3, which honestly is perhaps the most common, providing generic, textbook answers that are not specific to the scenario given in the question. These pitfalls just drain points from otherwise incredibly capable candidates. So always ground your answer in the specific context provided, and please double-check those edge cases.
By adopting this structured methodology, you now know exactly how to give the examiners what they are desperately looking for. You understand the core principles, that step-by-step procedural framework, the depth of critical analysis required, and exactly which traps to avoid. So, I will leave you with this final thought. Will you fall for the trap of superficial breadth, or will you apply analytical depth to your next current instruction register challenge? Think about how you'll approach your next past paper. Keep these frameworks in mind, apply them rigorously, and happy learning.